A water jet that leaves a nozzle at 60 meter per second at a flow rate of 120 kilogram per second is to be used to generate power by striking the buckets located at the perimeter of a wheel. Determine the power generation potential of this water jet. So we have the water jet and its velocity is given. Obviously, it has its own kinetic energy. In other words, it's mechanical energy that is capable of doing work, right? Rotating the shaft. So that means whatever the mechanical energy of that flowing fluid will be converted to mechanical work. Therefore, the power generation potential should be directly equal, the maximum power that can be generated by this fluid basically is directly equal to the kinetic energy of that fluid. Because we know the equation for mechanical energy of a flowing fluid per unit mass, right? Let's write it down. Good. That's incorrect. Okay. It is equal to flow energy related to the pressure plus kinetic plus potential. But in this case, flow energy is related to the pressure of the fluid that is capable of doing work, but there is no information about the pressure of that water jet right now, so it might be insignificant compared to kinetic energy. Therefore, they are not giving that information, and they are telling us to make the assumption to set this to 0. And potential energy is not also an energy here that is capable of rotating the shaft. And only mechanical energy, only form of mechanical energy that is capable of rotating the shaft seems like the kinetic energy. It has a significant contribution. And therefore the problem statement only gives us the velocity of that water jet. Therefore, mechanical energy per unit mass, we can say it is equal to the kinetic energy per unit mass of that water jet. And therefore, we write explicit form for this equation, which is velocity squared over 2. And velocity is 60 meter per second squared over 2. And again, we need to be very careful when we are dealing with kinetic and potential energies. Since the unit is meters squared per second squared, we need to multiply this with the unity conversion ratio to convert it to energy per mass. So we know that 1 kilojoule per kilogram is equal to 1000 meters squared per second squared. And with this unity conversion ratio, our final answer is 1.8 kilojoule per kilogram. So that is the energy of that water jet. It is per kilogram, it is 1.8 kilojoule for that water jet. And that is capable of doing work. That can be completely converted to work, the rotating the shaft. Therefore, the maximum power potential, therefore, is equal to the rate of mechanical energy. In other words, mass flow rate times mechanical energy per unit mass. And it is therefore mass flow rate is given to us 120 kilogram per second. Mechanical energy is given to us. We calculated that. And looking at the units, we have kilojoule per second, if you look at it carefully, which is the unit of power. Therefore, we don't have to do anything else here, not using any unity conversion ratios. Directly it should give me kilowatts because kilojoule per second is equal to kilowatts. So the answer is gonna be 260 kilowatts. Okay, so basically in this situation, the kinetic energy of that water jet can be converted to work completely, and in other words, the power of that fluid is determining the maximum power that can be generated, and that is rotating the shaft, and it is 216 kilowatts. Electric power is to be generated by installing a hydraulic turbine generator at a site 120 meters below the free surface of a large water reservoir that can supply water at a rate of 1500 kilograms per second steadily. Determine the power generation potential. Okay, so meaning that, remember the hydroelectric power plants, we have a water at a certain height, and the potential energy of that water will be able to rotate the shaft within the turbine because it is converted to work completely. So the potential energy is converted to work completely and rotating the shaft within the turbine, which is also attached to the generator, the shaft within the generator, and that is generating the electricity. Now, they're just asking the power potential of that water. So basically they're asking, in other words, the rate of mechanical energy of that water. Okay, water reservoir. So the first thing we need to do is calculate the mechanical energy per unit mass. That is gonna give me the energy of that fluid capable of doing work. So again, it is equal to flow energy plus kinetic energy plus potential energy. But here the main contributor to the mechanical energy of that water reservoir is its potential energy. And the flow energy and the kinetic energy, they are insignificant compared to potential energies. In fact, the problem statement, it doesn't give me anything about like the pressure or the velocity. It just gives me the height and the mass flow rate. So this tells me that mechanical energy of that fluid is equal to its potential energy. We can cancel out other terms, and which is equal to G times Z, and G is 9.81 meter per second squared, and Z is 120 meters. Again, the unity conversion ratio is, we need to utilize it here. We need to multiply this with 1 kilojoule per kilogram is actually equal to 1000 meters squared per second squared. This is going to help us convert the unit of potential energy, which is meters squared per second squared, to energy per mass, which is the unit of mechanical energy per unit mass. So it is 1.177 kilojoule per kilogram. All right. So what we said is the mechanical energy, the rate of mechanical energy is the power of that water reservoir. Okay, and we can find it by multiplying the mass flow rate with the mechanical energy per unit mass. This should be equal directly the maximum power potential. And we can calculate that because mass flow rate is given to us. And mechanical energy per unit mass is something we have calculated. I need to look at the units carefully. and kilojoule per second is the unit I'm looking for a power unit, and this is 1766 kilowatts. So basically that water reservoir has the power, has the potential to generate 1766 kilowatts of power. That's what it means basically. In this example, we have a river flowing around a lake at an average velocity of 3 meters per second at a rate of 500 meter cube per second. So when I first read it, I understand from the unit of 500 meter cube per second, they are giving me volumetric flow rate and the velocity of the flow, and as 3 meter per second. And what they're asking is find the mechanical energy of the river per unit mass. So remember, mechanical energy means the energy of the river that is capable of doing work, like rotating shaft at the bottom of the river, and the power generation potential of the entire river at that location. So take the density to be 1000 kilogram per meter cube. So basically when they're asking the power generation potential, they are asking the rate of energy flow, because the rate of energy flow, the rate of mechanical energy, is what is equal to the power of that fluid, the flow. And if they are giving me the density in the problem statement, that means I need to use it somewhere in my calculations. Now, from the sketch, we can understand that there is a potential change, potential energy change for the river, which is doing work, like rotating shaft at the bottom. So what we need to do is now calculate the mechanical energy of that fluid. And we can do that by using the equation we learned in the class. Let's write it down. This was mechanical energy per unit mass, right? And we learned that it is equal to its flow energy, potential energy, and the kinetic energy, sum up of those energies, flow and potential and kinetic energies. But the flow energy is related to the pressure of the flow, and there is no information given in terms of the pressure. It seems like it might be negligible in that case. So since the problem statement doesn't give me any information about that, I'm gonna cancel that term. I'm not gonna use that. And I'm just gonna use the potential energy and kinetic energy. The reason is they give me the velocity, so kinetic energy should be included. And there's also the potential energy, of course, the main contributor to doing work here. So therefore I'm gonna include potential and kinetic energies in my calculation. And potential energy per unit mass, we know that it is G times, let's say H, in this case 90 meter. And kinetic energy per unit mass is velocity squared over 2. Remember, always when we are dealing with potential and kinetic energies, we need to use a unity conversion ratio, because our calculations will give us the unit of meters squared per second squared, but we are looking for energy per mass unit, right? So let's plug in and let's see. So this is the value of gravitational acceleration. I should write all my units carefully. H is 90 plus 3 meter per second squared over 2. This has to be multiplied by a unity conversion ratio, because we know 1 kilojoule per kilogram is equal to 1000 meters squared per second squared. Because our units are gonna be meters squared per second squared, but mechanical energy per unit mass has a unit of kilojoule per kilogram. So this will help us to get the correct unit, which is now, this is the first part. The second part, the power generation potential. In other words, the rate of energy, the mechanical energy. The power. So when they say power potential, maximum power potential, okay, it is basically the rate of mechanical energy, and this should be equal to mass flow rate times mechanical energy per unit mass. And therefore, let's see, I know this term here, but I don't know mass flow rate, but the presence of density, be density given to you, should tell you that you need to use it in your calculation for the mass flow rate, because mass flow rate we know is density times volumetric flow rate, and density is 1000 kilogram per meter cube. Volumetric flow rate is 500 meter cube per second. They gave it to us, and this should tell us the mass flow rate should be 500,000 kilogram per second. Now we're gonna plug this in and this in here and calculate our power potential. Okay, so let's do that. Always include the units, because they will tell you if you are arranging the equation correctly and finding the right value at the end. Okay, this was the mechanical energy per unit mass. And now let's look at the units. Units should give me kilojoule per second, which, right, makes sense. Kilowatts. So $444,000 kilowatts, or 444 watts. Okay. A hydraulic turbine has 85 meters of elevation difference available at a flow rate of 0.25 meter cube per second, and the overall turbine generator efficiency is 91%. Determine the electric power output of this turbine. So when we look at it, we remember what we learned about hydroelectric power plants, that we have a potential energy of a fluid, and it is gonna rotate the shaft in the turbine. That mechanical energy of that fluid is gonna be converted into the basically the mechanical energy by rotating the shaft, and that shaft inside the generator, which is the output of the turbine but input of the generator, it's gonna generate electricity. And we have an equation for the overall turbine generator efficiency, and let's write it down, because we know the efficiency of turbine generator combined system is always the efficiency is output over input, right? And output of the generator is the electric power, and input to the turbine is the mechanical energy. or the rate of mechanical energy. We can use the rate form of the energies, and because they're asking for the power, and so instead of electric work I use electric power in my numerator in the equation. So here what we know this term is given to me, and it looks like I would be able to calculate this because the potential energy information given to me. And of course they're asking for this term, so I might be able to use this equation to calculate what they're asking. So let's rearrange it. So the efficiency times the rate of mechanical energy should give me the electric power. Instead of the rate of mechanical energy, I can write mass flow rate times mechanical energy per unit mass. And mass flow rate I can calculate from density times volumetric flow rate, because they give me the volumetric flow rate and density. I can accept it as 1000 for water. And mechanical energy per unit mass is, remember, it is equal to flow energy plus kinetic plus potential energies. But the problem doesn't tell us anything about the pressure and the kinetic energy. I would assume they are not significant compared to the potential energy. In here, the potential energy is actually converted to work. It is doing the work. So mainly that is the one that is responsible for doing the work. Therefore, and also since the problem statement doesn't give me any information about velocity or pressure, I'm just gonna say the mechanical energy is directly equal to the potential energy of that flow. So it is gravitational acceleration times the height. Okay, and that should give us the electric power. Now I know every term in here. Okay, so I know the efficiency is 0.91 because 91% they say, and density I accept it as 1000 kilogram per meter cube. Usually the problem statement should give you that information. And the volumetric flow rate is given to us 0.25, and gravitational acceleration is 9.81. Okay, and we continue that equation. Is the height of that water is 85 units. Seems like they are making sense. Now at this point we're gonna do a calculation, but I need to be very careful what is gonna be the unit we are ending up with. So if we look at it carefully, kilogram meter per second squared is Newton. Newton times meter is joules. Joules per second is watts. So very good. What I'm looking for was a power term, power unit, and it is giving me power unit, but in terms of watts. And if I want to convert to kilowatts at the end, I might have to divide all this equation to 1000, which is okay. We get the value of 190 kilowatts. Okay. Determine the energy required to accelerate a 1300 kilogram car from 10 to 60 kilometer per hour on an uphill road with a vertical rise of 40 meters. So in this case, looking at the question statement, I can see that basically kinetic energy is changed because the velocity is increased from 10 to 60 kilometer per hour, and also the potential energy has changed So vertically. Therefore, we are doing work to accelerate an object, and we are doing work to raise an object. So therefore, we are changing the potential and the kinetic energies. So remember the work to accelerate. Okay, let's use black color. Work to accelerate is equal to the kinetic energy change because the work we put changes the kinetic energy, and that is equal to 1/2 mass times velocity squared difference. And also we need to calculate work to raise an object, which is the change in its potential energy, and that is mg delta z, or z2 minus z1. So we need to calculate these and then sum them up to find the total work or total energy required in this situation. Now the units are kilometer per hour. So what I would do is, I don't want to work with those units. I'm going to convert those to meter per second. So we can do it easily. 10 kilometer per hour. 1 hour is 3600. Oh, we need to write it in the, I'm sorry. 1 hour is 3600 seconds. So this way hours cancel. And we need to also convert this kilometer to meters, which is 1 kilometer is 1000 meters. So this way, this, oh, not that one, this one goes right. So we end up with a unit meter per second. So if you do that, you should find approximately 2.8 meter per second. Do the same process, apply the same process to 60 kilometers per hour, and it should give you I think it is 16.7. So it is easier to work with these units. And now let's calculate the work to accelerate an object, which is the change in its kinetic energy. Mass is given to us as 1300, and velocity squared difference, unit is meters squared per second squared. And from here we can calculate it, but let's look at the unit to make sure. Kilogram meter per second squared is Newton, right? This is Newton times meter. There is one more meter here. So Newton times meter is joules. Joules per, joules directly, right? Kilogram meter per second squared is Newton. Newton times meter is joules. If I divide the overall equation to 1000, I should find it in terms of kilojoules. So this should be equal to 175.5 kilojoule. Okay. Now let's find also work we do to raise an object, which is its potential energy change. Mass is 1300 kilogram times gravitational acceleration meter per second squared, and our change in height is 40 meters. And then of course dividing this to 1000 also, because the unit is Newton times meter, joules. So we divide it to 1000, you get 510 kilojoule. So we can sum those up to find the total work necessary to change the kinetic and potential energies of that car. Is total is 175.5 plus 510 kilojoule is equal to 686 kilojoule. That's your final answer. A river flowing steadily at a rate of 175 meter cubed per second is considered for hydroelectric power generation. It is determined that a dam can be built to collect water and release it from an elevation difference of 80 meters to generate power. Determine how much power can be generated from this river water after the dam is filled. So this is very similar to the previous questions we've done. So there is a hydroelectric power plant and a river that is at a height of 80 meters, and we wanna extract its power basically, but its main power comes from the its potential energy, because its potential energy can be converted to 100% to the work or the power. So therefore all we need to do here is calculate its mechanical energy, and from its mechanical energy, the rate of mechanical energy of that flow is gonna give us its power. So similar to what we have done before, we are calculating the mechanical energy, which should be equal to its potential energy, because mechanical energy again is equal to flow energy, kinetic and potential energies, but no information is given to us about the flow energy and the kinetic energy. So those terms should be insignificant, because the main contributor to the power generation should be the potential energy of that river. So this is again G times Z or H, and then 9.81 meter per second squared. Z is 80. As for kinetic and potential energies, we always use the same unity conversion ratio, because we need to convert meter squared per second squared to kilojoule per kilogram, and the final answer is 0.7848 kilojoule per kilogram. So that is the mechanical energy of that water from the river per kilogram. It has the energy of 0.7848 kilojoule. So the next thing we do is convert this. We're not going to convert it, but we're going to use it in the equation where we calculate the energy flow rate, mechanical energy flow rate, which is equal to mass flow rate times mechanical energy per unit mass. This should be equal to the maximum power potential, because it can be completely converted, that mechanical energy of that fluid. And here the mass flow rate can be found from density times volumetric flow rate. Density is 1000 kilogram per meter cube. Volumetric flow rate is 175 meter cube per second. Let's check it. Good. And then we continue, right? We're gonna add the mechanical energy to this, which is 0.7848 kilojoule per kilogram. Okay, so here the kilograms cancel and meter cubes cancel, and we are left with the unit of, if you look at it, kilojoule per second, which is the unit that we are looking for, and it will give us in terms of kilowatts. And if we divide that to 1000, it should be in terms of megawatts. And let's do it. All right, that's the final answer. Basically, that is the power potential of that river. A geothermal pump is used to pump brine whose density is 1050 kilogram per meter cube at a rate of 0.3 meter cube per second from a depth of 200 meters. For a pump efficiency of 74, determine the required power into the pump and disregard frictional losses in the pump and assume the geothermal water at 200 meter depth to be exposed to the atmosphere. All right, so here again we are looking at pump efficiency, and we need to remember what is the equation for pump efficiency. So pump efficiency, always any type of efficiency, we have output over input, and input to the pump is the electric work, electric power, and that is what is rotating the shaft within the pump and changing the energy of that fluid, and in this case it's changing its potential energy, and therefore the output is going to be the mechanical energy change. It is going to change its mechanical energy, or the rate of mechanical energy if we use in terms of change with time. So they give us this one and we are trying to calculate this, so therefore I need to figure what this term here is, and we know that we can calculate that from mass flow rate times mechanical energy change per unit mass. And in this case, again, a flow energy or kinetic energy, these are insignificant compared to the potential energy change achieved with the pump, because they didn't give us any information about pressure, and then the kinetic energy velocity changes. What they said is 0.1 and 0.2 both are upon to atmospheric pressure, so the pressure is very close at 0.1 and 2, therefore potential pressure difference is basically 0 there, so therefore we can ignore those terms and say the mechanical energy change per unit mass is only equal to the potential energy change per unit mass, and therefore that is G times delta Z, which is basically 200 meter in this case, and then mass flow rate is of course density times volumetric flow rate times G times delta Z. Okay, so we can plug in the information we know, because we know density can be assumed to be, or we cannot assume, they give it to us, right? We can just write it down. And volumetric flow rate is something they give in the problem statement, and G is this, and this is 200 meters. The units, let's take a look at it. Kilogram meter per second squared is Newton. Newton times meter is joules. If I divide the overall equation to 1000, I should get it in terms of kilowatts. Wait a second, what am I missing? Oh, this is, we are missing a second here, right? Because that is volumetric flow rate and the unit should be 0.3 meter cube per second. Now it makes sense because it becomes joules per second, which is the unit I'm looking for, right? I'm looking for power unit. Therefore, now the calculation is correct with the correct units is 618 kilowatts. Okay, this is basically the mechanical energy change achieved by the pump, and we need to plug this in information here in this equation. The pump efficiency is 0.74, means 74%, and then we are trying to calculate the electric power, and mechanical, and the rate of mechanical energy change is 618 kilowatts. And from here you should be able to calculate the power necessary that we need to put into the pump should be 835 kilowatts. This way we can achieve this amount of potential energy change in the fluid. A 4 kilowatts resistance heater in a water heater runs for 2 hours to raise the temperature of the water to the desired level. Determine the amount of energy used in kilojoules. So when they give us power and the time, I always remember what is the equation for the electric power is electric work over time. And in this case, they are giving us the power, which is 4 kilojoule, which is 4 kilowatts, which is 4 kilojoule per second. And the time is 2 hours. 2 hours is 7,200 seconds. And I need to find the electric work. So you just have to solve it. And it should give you kilojoule. So a force of 1.2 kilonewton moves a truck with 60 kilometers per hour up a hill. What is the power? Here we have two givens, a force and velocity. And from those givens, what is expected is to figure out the equation for the power here. And in fact, the equation for the power is force times velocity. We can prove this looking at the units. All right, so basically force is 1.2 kilonewton. I'm gonna add some unity conversion ratios here. 1 kilonewton is 1000 newton. And 1 newton is 1 kilogram meter per second squared. And we need to multiply this with 60 kilometer per hour, but I want to change the unit to, of course, meter per second. So looking at this, okay, so the velocity is actually 16.67 meter per second. And as we continue with our power calculation, we can add now 16.67 meter per second. Now you need to take a look at the units here. Okay, let's choose a different color, maybe this. So this cancels out, this cancels out. What we left up with is units. If you look at it and if you do the calculation, okay, this times that, it should be 20,000. The units are kilogram meter squared per second cubed. So if you look at this carefully, there is kilogram meter per second squared here, which is Newton, times there is, actually there's second cubed, right? Because this times that. So there is therefore kilogram meter per second squared, which is Newton. There is meters, Newton times meter, and there's second. So it is actually joule per second, which is watts. So the answer you found is actually 20,000 watts. At winter conditions, a house is projected to lose heat at a rate of 17,584 joule per second. The internal heat gain from people, lights, and appliances is estimated to be 1,758 joules per second. If this house is to be heated by electric resistance heaters, determine the required rated power of these heaters to maintain the house at constant temperature. So, when I read this sentence, I understand that there are energy interactions. So there is a house, there is energy getting into it, and there is also energy loss. But what we are trying to do is keep the temperature constant. To be able to keep the temperature constant, the rate of energy flow getting in has to be equal to the rate of energy flow getting out. Therefore, the temperature inside stays the same. So basically, this will keep the temperature inside the same. So when we look at what is getting in given to us this much of power, okay, but what is getting out is much more than that. That's why we need to also put in some resistance heaters. Okay, so if we look at the house, therefore the energy is getting in with the rate of this, but getting out at a higher rate. Now that means in order to keep the temperature the same, okay, we need to also introduce more energy, more power with the electric energy. Okay, so therefore, how much of this, of course, is this much. Okay, when you calculate it, it is or okay, that's it. At a certain location, wind is blowing steadily at 10 meters per second. Determine the mechanical energy of the air and the power generation potential of a wind turbine with a 60 meters diameter blades at that location. take the air density to be 1.25 kilogram per meter cubed. So there is wind, air flowing, and it has a velocity. So therefore that kinetic energy of the wind basically determines its mechanical energy and its power. So let's calculate therefore the mechanical energy per unit mass for that wind. Here potential energy and flow energy is insignificant, and therefore only they give us the velocity, which relates to its kinetic energy. So this is gonna be equal to the kinetic energy, which is 1/2 velocity squared, which is of course remembering the unity conversion ratio always when we are dealing with kinetic and potential energies. And it gives us 0.05 kilojoule per kilogram. Okay, so this is the mechanical energy per unit mass for the wind. So in 1 kilogram of this wind, there is an energy of 0.05 that is capable of doing work, meaning rotating the wind turbine, that is capable of rotating the wind turbine. So now this is gonna help us to calculate the rate of mechanical energy, which determines its power. So mass flow rate is density times volumetric flow rate times mechanical energy. Now, they didn't give us volumetric flow rate. They gave the density 1.25. But they tell us about the diameter. So diameter should give you information about the area. And if you remember, instead of volumetric flow rate, we can replace volumetric flow rate with velocity times area. So now we can use that equation because we know that density is given, velocity is given. Instead of area, I can write pi d squared over 4 and times, of course, the mechanical energy per unit mass. Together, if we calculate from this equation, what we're gonna find is the maximum power potential, because all that mechanical energy of the wind can be converted to the work completely. And if it is completely converted to the work, that is gonna tell you the maximum work potential or maximum power potential for the wind. So let's plug in the numbers and calculate this. Density is 1.25 kilogram per meter cube. Velocity is 10 meter per second. And diameter is 60 meter over 4. And we also need to find the mechanical energy, right? We need to, multiply the mechanical energy here, but it was equal to this value that we have found. We just need to include that. Okay, if we look at the units carefully here, you're gonna see this is meter cubed here, cancels out this, and the kilograms also go. We end up with kilojoule per second, which is the power unit that we are looking for. So if you calculate this, you will find 1770 kilowatts. So this much of power can be generated by this wind turbine. Water is pumped from a lower reservoir to a high reservoir by a pump that provides 20 kilowatt of shaft power. The free surface of upper reservoir is 45 meter higher than that of the lower reservoir. If the flow rate of water is 0.03 meter cubed per second, determine the mechanical power converted to thermal energy during this process due to friction and the pump efficiency. Okay, let's sketch it. Basically, there is a pump, right? And then it takes shaft power in, because we know how pump works. It gets power in and it changes the mechanical energy of the fluid, right? And the free surface of the upper reservoir is basically, it says 45 meter higher than that of the lower reservoir. If the flow rate of the water, they say basically the volumetric flow rate is 0.3. So here basically, if you take a look at what is the efficiency equation for the pump, we know that it's got gonna be 100% efficiency. And what is getting into the pump is the shaft. And what is it getting out and changing is the mechanical energy. Now, first of all, at the second part, they're asking us to find this efficiency, but they are giving us only this, right? And some way, if we can find this part, we can find the efficiency, and we can only also find energy loss due to friction, because the reason we don't have 100% efficiency is whatever the energy we are putting in, like in this case, the power we put in is 20 kilowatts, but what is getting out is going to be less than that. And that difference is the loss. Okay, so let's basically calculate the rate of mechanical energy change, which is equal to mass flow rate times mechanical energy change per unit mass. In this case, the main contributor is the potential energy change. And that is mass flow rate times G times H. Instead of mass flow rate, we can say density times volumetric flow rate times G times H. Now, let's calculate it. Density is 1000 kilogram per meter cubed. Volumetric flow rate is 0.03. And gravitational acceleration is this. And then 45 meter is the height. Of course, as always, we need to use the unity conversion ratio. Kilojoule per kilogram is equal to 1000 meters squared per second squared. And when we do these calculations, we find 13.2 kilowatts. So basically, the shaft work is 20 kilowatts, but the mechanical energy change is 13.2. So there is some loss there. And how much? So this is the power lost due to friction. Okay, and but we can also calculate the efficiency, because efficiency of the pump is going to be basically 13.2 over 20. This is 0.66 or 66%. Okay, so in this question we have an oil pump drawing 44 kilowatts of electric power while pumping oil with density of 860 kilogram per meter cubed at a rate of 6 meter cube per minute. The inlet and outlet diameters of pipe are 8 centimeter and 12 centimeter, respectively. If the pressure rise of oil in the pump is measured to be 500 kilopascal and the motor efficiency is 90%, determine the mechanical efficiency of the pump. So when I read this problem statement, I notice certain things. For example, they talk about the pump and the motor. So they're actually talking about the combined system of pump and motor. So let's sketch that. So there is the pump attached. Okay, so let's write it down. Here is our pump. And there is the motor. So let's think about what is happening here. We provide electric power to the motor, and it's rotating a shaft, which is the shaft getting into the pump. And in the pump, this shaft is changing the energy of a flowing fluid. Okay, so now when I first read it, I would write what they're asking for. So they're asking for the pump efficiency, right? Output over input. So output here is the mechanical energy change, or the rate of mechanical energy change. The input is the shaft power. Okay, so when we think about how we can calculate the mechanical efficiency of the pump, we need to know the mechanical energy change and the shaft work that is, or the power that is getting in. Let's also write the motor efficiency because they give that value to us. That means we need to work with it. So let's write it. In the motor, there is, what is the output is the shaft. This shaft output is what is getting into the pump. So they are actually the same thing. But in one of them it is the output, in one of them it is the input, but they are the same. So output is the shaft power, and what is getting in is the electric. Now looking at this, they give me this value. They say it's 90%. And they also give me the electric power here, 44. That tells me I should be able to calculate what is the shaft work output. Let's do that. Yes, so this is 39.6 kilowatts. Now, that tells us we have found the shaft power output. In other words, the shaft power input that is getting into the pump. Now, since we also know this one right now, and this value is, and only thing we need to do here is calculate the mechanical energy change of the flow due to the pump, right? Due to the shaft work that is changing the mechanical energy of that fluid in the pump. And I think we can calculate that because they talk about the pressure difference, pressure change. They give us also diameters of the pipe inlet and outlet. So at the inlet it is 8 centimeter, outlet is 12 centimeter. If I see the question gives me diameter information, that tells me that I need to calculate the area. Okay, and if I'm going to calculate the area, probably I'm going to use it in the velocity times area is equal to volumetric flow rate equation. And since also they give you the volumetric flow rate, you should be able to calculate inlet velocity and exit velocity from that equation. So that means there is some kinetic energy change and the pressure change. So it is possible we can calculate the mechanical energy change and the rate of mechanical energy change. So let's do that, okay? So first of all, we know that, let's write it down, black colors. Okay, so here we say the rate of mechanical energy change is equal to mass flow rate times the rate of mechanical energy change per unit mass. And this is equal to, of course, we know this term is equal to the change in the flow energy, change in the kinetic, change in the potential energy. And seems like only terms that are significant are the flow energy and the kinetic energy here, because they didn't give us any information about the potential energy change. So I'm gonna put for the mechanical energy change per unit mass, I'm gonna put a flow energy term per unit mass, which was delta P, pressure change over density, plus the kinetic energy change, right? Now, mass flow rate, do they give it to us? Let's look at it. They didn't give us mass flow rate, but they did give me density and volumetric flow rate, which I can easily calculate mass flow rate from there. So pretty much this is given. Pressure change is also given. Density is given. So we need to figure out actually the kinetic energy change. Let's see how we can do that. Because kinetic energy change is equal to 1/2 velocity 2 squared minus velocity 1 squared. Well, we don't know the velocities, but here is the thing. We know the volumetric flow rate throughout the pump. So this should be equal to V1 times area, or this should also be equal to V2 times area, because the volumetric flow rate throughout the system is the same. Density is the same. Mass flow rate through the pump is the same at the inlet and the exit. But what is changing is the cross-sectional area is different from the inlet and the exit. They are different. And that is causing a change in the velocity. So therefore, thinking about this, and also remember how we obtain these equations, right? Remember in the class we learned why velocity times area is equal to volumetric flow rate, and you can also prove this to yourself looking at the units of these terms. But the idea here is we can actually solve them to find the velocity at the inlet and the exit. And let's do that. But I need to add a page here. Let's do that. Okay, so basically velocity is the volumetric flow rate. Volumetric flow rate is, instead of area, first of all, we can write pi d squared over 4. And volumetric flow rate is 0.1 meter cube per second. They give it to us in the problem. And of course, they give in terms of centimeter the diameters, but we need to convert them to meters. So the pi times 0.08 meter squared over 4. Okay, so this should give you the first velocity to be 19.9 meter per second. And the next thing, we do the same to the second velocity. And again, 0.1 pi over 4. And this is 8.84 meter per second. All right, so very good. We learned the velocities now. And if you can understand how I'm approaching things, I'm looking at the givens and I'm looking at what is being asked. Since I'm familiar with the equations, givens are guiding me in the solution. I can figure out, for example, if they give me area or diameter, I think that is the equation where I'm going to use it, right? And to find the velocities, I can understand that from there. So now after this, we know the velocities. We can calculate therefore the kinetic energy change. Okay, let's do that. So the kinetic energy change remember, we need to use the unity conversion ratio. And do your calculation. The answer is okay. So the next thing is, after we find the kinetic energy, we go back. We need to plug everything in this equation and do our calculation. Okay, let's remember mass flow rate times, okay, delta P over density plus kinetic energy change, right? Let's make sure. Okay, now here instead of mass flow rate, it is density over, of course, let's write down this is the mechanical energy change with respect to time. So instead of mass flow rate, I write density times volumetric flow rate, delta P over density, and then kinetic energy. So the density is given to us, it is 860 kilogram per meter cube. Volumetric flow rate is 0.1 meter cube per second. Pressure change is 500 kilopascal over density. And the kinetic energy change, which is actually minus, right? So we should just put the minus 0.159. And the unit is kilojoule per kilogram. Okay. So let's take a look at the units. So this is actually kilojoule per kilogram too, because kilopascal times meter cube is kilojoule, and then kilojoule over kilogram. Both units are the same. Here it is kilogram per second, and kilograms cancel out. We left with kilojoule per second, which is actually the unit we are looking for. And if you do the calculations right, you should get 36.3 kilowatts. All right, the next thing we're gonna do is we found the rate of mechanical energy change, and we need to put this into the equation we previously have shown right there. And we're gonna divide this to this number to calculate the efficiency. So it's So efficiency of the pump is therefore 91.8%. Alright, so water is being heated in a closed pan on the top of a range while being steered by a paddle wheel. During the process, 30 kilojoule of heat is transferred to the water and 5 kilojoule of heat is lost to the air. And the paddle wheel work amounts to 500 Newton times meter, which is joules. Determine the final energy of the system if its initial energy is 12.5. Okay, same idea here where energy interactions taking place and they are changing the energy of our system, and the only energies that can get involved in energy interactions are heat and work, and they are changing the energy of our system from one point to another, right? State 1 to state 2. So basically, if we sketch what is going on, we have water being heated while being steered by a paddle wheel. Okay, so we can say that is shaft work getting in the amounts of 500 Newton times meter, which is joules. And of course, this is in terms of kilojoules, 0.5 kilojoule. Now, another information about the energy interactions is 30 kilojoule of heat is transferred to the water. So heat is getting in, crossing the boundaries, 30 kilojoule. I just had to make sure all of them are in the units of kilojoules so we don't make a mistake. And another type of energy interaction is also heat. They say 30 kilojoule is getting in, but 5 kilojoule is getting out. Okay, let's sketch that too. The paddle work amounts to 500, we said that, and determine the final energy of the system. So always energy balance. We start with the same form of it. because we understand now whatever the energy interactions, they are changing my energy of the system. It has a certain energy at the first state and it is changing to another energy at the second state because of these energy interactions. And we say energy getting in minus the energy getting out is equal to the change in the internal energy of our system. And here energies that are getting out, if we want to write it more explicitly, the shaft work is getting in and heat is getting in, but what is getting out is only heat, and that is changing the internal energy. So now let's write it down. Shaft work is 0.5 kilojoule. Heat getting in is 30 and heat getting out is 5. They are changing the energy of our system, and we know they give us the initial internal energy to be 12.5 kilojoule, and from here we can calculate the second state internal energy. And when you do your calculations, it should be 38 kilojoule. So the engine of a 1500 kilogram automobile has a power rating of 75 kilowatts. Determine the time required to accelerate this car from rest to speed of 100 kilometers per hour at full power on a level road. Okay, so basically they give us the mass and the power and time required to accelerate. So basically what they're telling us is if we want to calculate the time only exists in that power equation that is required to accelerate the car. It is basically work over time, right? Therefore, I need to know the power, which I know they give it to me, 75. And if I want to calculate the time from here, now we need to know the work to accelerate the car. And work necessary to accelerate the car is equal to its kinetic energy change, which is 1/2 mass times V2 squared minus V1 squared. But initially it was at rest. So therefore 1/2 mass times velocity 2 squared. Before I plug in the velocity to my equation, I would convert the unit, which is 100 kilometer per hour, to meter per second. Therefore, you need to, of course, multiply this with 1 hour is 3600 seconds and 1 kilometer is 1000 meters. So here you find approximately 27.8 meter per second. Okay, so now it is easier to work with. In our equation to calculate the work necessary to accelerate the car is 1/2 and the mass is 1500 and the velocity is 27.8 meter per second squared. Okay, so the unit is basically, let's take a look at it. Mass time velocity squared. Kilogram meter per second squared is Newton. Newton times meter is joules. So this is the energy unit, which is correct. And if we divide it to 1000, we can find it in terms of kilojoule, and that should be 578.7 kilojoules. Okay, now we found this, and what we need to do is divide this to the power to calculate the time, right? According to this equation, I'm gonna divide this because you can solve this for time, right? And that is work over power. So take the work and divide to the power, which is 75 kilowatts, meaning 75 kilojoule per second. And this should give you 7.72 seconds. Work is done on a closed system. The mass of the closed system is 0.5 kilogram. By rotating a shaft in the amounts of 10 kilojoule. The time is 20 seconds. Determine the work per unit mass, which is work over mass, and the power, which is work per time. All right, so since we know the equations, work is 10 kilojoule, mass is 0.5 kilogram, and the work per unit mass is therefore 20 kilojoule per kilogram. And the power is work per unit time. Alright, so in this question we have heat is lost from a system in the amount of 3 kilojoule. I would sketch it. Heat is getting out. If the energy of the system is decreased by 5 kilojoule, meaning the change is -5, what is the work interaction? Okay, so I'm not given the information if work is getting in or getting out of my system, so I don't know. But I can start with writing the general energy balance that we always do when there is a problem as such. We write energy getting in minus the energy getting out. These energy interactions taking place in the form of heat and work can change the energy of my system. That's it. Now, energy can get in the forms of heat and work, writing an explicit form here. And energies can get out same way, heat and work, because heat and work are the only type of energies that are involved in energy interactions, and they are changing the energy of our system. Now for sure we know that heat is not getting in because they say the heat interaction is, I'm sorry, this I wrote wrong here. So this has to be energy is getting out in terms of heat and work. So when I'm talking and thinking and writing at the same time, sometimes I make mistakes. Okay. So for sure we know that there is no heat getting in, right? And heat is getting out, and we know it is in the amounts of 3 kilojoule. And the change in the energy of the system is -5 kilojoule. Now, we don't know if the work is getting in or getting out. But if work is getting in, that has to be in the amount of minus 2 kilojoule. If you calculate it, this is not possible because the work and heat terms in this equation, all of them have to be positive numbers. And therefore seems like that is not the case in this situation. Therefore, I would say this is also not happening. I would make that assumption. But work is only getting out. So if that is the case, the work interaction therefore should be 2 kilojoule. Okay, the work that is getting out is 2 kilojoule and the heat that is getting out is 3 kilojoule. So basically heat and work taking out 5 kilojoules of energy. Therefore your system's energy decreased 5 kilojoules because it is taking out energy from your system by heat and work. So that makes sense. Okay, heat is transferred to a closed system in the amount of 13 kilojoule, while 8 kilojoules of electric work is done on the system. There are no kinetic and potential energy changes. What is the internal energy change of the system? Again, we start with writing our energy balance. You can first sketch and say heat is transferred. So Q in is 13 kilojoules and electric work in is 8 kilojoule. So energy can only be carried with heat and work to our system and in and out of our system, right? So therefore these energy interactions should be changing our energy of our system as they cross the boundary of our system. So again, we start with writing the general form of energy balance. Energy getting in minus energy getting out is equal to the change in the energy of our system. But the change in the energy of our system is equal to its internal energy change, kinetic energy change, and potential energy change. But we learned that these terms go to zero when our system is stationary. And in fact, the problem statement says